In this video, we're going to go over the mean or expected value of a probability distribution. Now, the mean of a probability distribution is literally the average outcome of the experiment represented by the probability distribution per trial. Some notation down here: the mean of a probability distribution is also referred to as its expected value, as we have stated up here, and it's denoted by the symbol mu for mean that we've seen before, or E of x. That's our expected value notation. Now here's how we calculate the mean given a probability distribution. So to evaluate the mean mu, we simply multiply each possible outcome x by its probability and we sum. So that's what this tells us right here. You notice we take each outcome x, multiply by its corresponding probability, and then we sum all of those up. So that's how you calculate the mean. Now we're going to take a look at an example where we use this formula first, and then we'll look at an example where we motivate this formula so you understand why we use it. Now for this example, we have a car salesman, John Barkdale, sells new cars, and he has developed the following probability distribution for the number of cars he expects to sell on any given Saturday. So for example, down here we read this table as follows. He can expect to sell 0 cars on a given Saturday with a 0.1 probability. So on any given Saturday, there is a 10% chance that he will sell no cars. On any given Saturday, there is a 0.2 probability that he will sell 1 car, or a 20% chance that he will sell 1 car, a 0.3 probability of selling 2 cars, a 0.3 probability of selling 3, and a 0.1 probability or 10% chance of selling 4 cars. So that's the probability distribution for the number of cars he can expect to sell on any given Saturday. Notice when we sum all of these, we do get 1. So now what we want to calculate is the mean number of cars that he sells on Saturdays, or the expected value. So all we have to do is evaluate this quantity right here. So what we do is we multiply each of these together, x times p of x, and we sum. So we go 0 times 0.1, 1 times 0.2, 2 times 0.3, 3 times 0.3, 4 times 0.1. That's what we have written right over here. And when we evaluate this quantity right here, we get 2.1. So on average, John sells 2.1 cars on Saturdays. Let's take a look at an example where we motivate this formula now so we understand where it comes from. So here's a game example. So suppose we play a simple game. You roll a 6-sided die, and if the die comes up 1 or a 2, you win $2. But if it comes up 3, 4, 5, or a 6, you lose $1.50. So let's calculate the mean outcome per turn for this game, or we want to calculate the mean or expected value for our probability distribution that we have pictured here. Now this is our probability distribution. Notice that our outcomes can either be a 2, we win $2 with a probability of 1/3. Where does that 1/3 come from? Well, you have 2 out of 6 ways that you can win, a 1 or a 2. So that's 2 out of 6. This is 2 out of 6. That reduces to 1/3. You lose $1.50 if you get a 3, 4, 5, or a 6, and the probability of losing is 4 out of 6. and that reduces to 2/3. So here is our probability distribution. Now, to understand why we do this formula down here for the mean, think about it like this. Suppose we play this game a lot, like I'm going to pick the number 600 times just so the numbers work out nicely. Suppose you played this game 600 times. How many times would you expect to win? Well, you would expect to win 1/3 of the time, right? So if you multiply 600 times 1/3, that's 200. You would expect to win 200 times out of the 600. And then, of course, you would expect to lose 400 times. Notice this 400 we get by, well, you can subtract 200 from 600, of course, or you can multiply 600 by 2/3, your probability of losing, and you get 1200 over 3, which is 400. So if you played the game 600 times, you would expect to win 200 times and lose 400 times. So therefore, your average winnings per turn would be this. We have 200 times where we win $2. So if we take 2 times 200, these would be the number of winnings, and we add it, there should be a little plus in here, we add that to 400 negative 1.5s, right? So we multiply negative 1.5 times 400. So this quantity up here in the numerator of this fraction, this quantity right here, represents our total winnings or losings for the 600 times that we played the game. Now when we divide that by 600, that's going to give us our average outcome per turn. Now notice, if we split this fraction apart, you see what we get is we're just going to split it right at that plus right here. So we're going to write it as 2 times 200 over 600 plus negative 1.5 times 400 over 600. Remember, we're using the rule that A plus B over C equals A over C plus B over C. That's the rule we're using to break that fraction apart. And now this 200 over 600, notice that that reduces to 1/3. And the 400 over 600, that reduces to 2/3. Well, look at what we have here for our average outcome per turn. 2 times 1/3, that's 2 times 1/3 up here in our table, plus negative 1.5 times 2/3. Negative 1.5 times 2/3. That's exactly the formula, the sum of x times p of x. And when we evaluate this quantity right here, we get negative 0.33. And so we see, by looking at it from the point of view of playing many, many times, we see how this formula, the summation of x times p of x, is coming out. So that's why we use this formula for the mean of a probability distribution, or its expected value. Now notice something else about this game. We came up with a negative expected value, negative 0.33. What that means is, from the player's point of view, this is a losing game. So in other words, if the player played this game many, many times and they calculated their winnings or losings, so winnings or losings, if they came up with a negative number, we'll just say win or loss, total win or loss, and they divided by the number of times they played, they would come up with a number very close to negative 0.33, which means on average, each time they play this game, they can expect to lose 33 cents. That's what this means. Let's take a look at another example here. Let's actually calculate the expected value for a real-world lottery problem. So the PA daily number is played by selecting 3 balls from 3 separate bins, each containing 10 balls numbered 0 through 9. We went over a problem like this previously. So for this problem you have 3 bins. Each bin contains 10 balls numbered 0 through 9. And the lottery selects 1 ball from each bin. Now, one way to play this game is to box 3 different numbers like 5, 3, 8, meaning that you win if you match the numbers drawn in any order. Now, a ticket costs $1 and you get $80 back if you win. Let's develop a probability distribution for this game. And let's also calculate the game's expected value. And let's take note of something else. A game is said to be fair if it favors neither the player nor the house, which is the same as saying that the expected value is 0. So we're going to determine what the payout should be. So in other words, what this number should be here for the expected value to be 0. As we'll see, the expected value for this game is not 0, it's actually negative. So the game favors the state of Pennsylvania. It does not favor the player. That's to be expected because after all, Pennsylvania wouldn't have a lottery if it was losing money. So all lotteries have a negative expected value from the player's point of view. So here's how we set this problem up. Now recall from our previous discussions that the number of possible outcomes for this lottery is 10 times 10 times 10 or 1,000. You get that just by multiplying the number of selections from bin 1, which is 10, times the number of possible selections from bin 2, which is 10, times the number of possible selections from bin 3, which is 10. So we have 1,000 possible outcomes. Now, you selected the number like 538, 3 different numbers. Now, how many arrangements are there of 538? In other words, how many times is 538 included in this 1,000 over here? Well, the number of arrangements of 538 is going to be 3p3, which you can evaluate is 6, or it's also 3 factorial, right? If you think of, okay, I have 3 slots to fill with these numbers. I have 3 ways to fill the first slot, then I have 2 ways to fill the second, then 1 for the third. When you multiply these together, by the fundamental rule of counting, there are 6 possible arrangements of the numbers 538. So in other words, your probability of winning is going to be 6 out of 1,000. Now your probability of losing then is 1 minus 6 out of 1,000, or 994 out of 1,000. Okay, so now let's set up our probability distribution. So now you will lose $1 with a probability of 994 out of 1,000. Right? When you bought the ticket, you put $1 in. If you lose, you don't get anything back. So you lost your dollar that you used to buy the ticket. Now if you win, you get back $80, but you don't get back that dollar that you bought the ticket with. So technically, you only get back $79, or that's actually, the 79 is your net winnings. You paid $1 for the ticket, the state gave you back 80, so actually you only won $79. And the probability of that is 6 out of 1,000. So here's our probability table. Now, to calculate the expected value, all we need to do is multiply these together and add. And let's do that in the next slide. So then here is our expected value. We just multiply these together. -1 times 994 over 1,000 plus 79 times 6 over 1,000. You can evaluate that on your calculator. You will come up with 52. Okay, so this is a losing game from the player's point of view. What this number means is that if you played the Pennsylvania daily number many times and you kept track of your total winnings or losings, the total amount you won or lost, you kept track of this number, the total amount you won or lost, and you divided by the number of times you played, you would come up with a number very close to negative 52. Which also means that if you played the game many times, in the long run, you would expect to lose 52 cents each time you play this game. Or, in the long run, for every dollar you put into the game, you can expect to get back only 48 cents. Now, let's calculate what the payout by the state should be for the game to be fair. So to find the payout for the game to be fair, what we do is we replace this number right here with a p, a variable p, and we set this quantity, instead of negative 52, we set it equal to 0, and we solve for the p value right here. And that'll determine what the payout should be so that the game is fair. The expected value is 0. So here's our equation set up right here. And we just have to solve that. So to solve this for p, we move this over to the other side. It will become a positive then. And what we end up with, I'll just write it up here, we end up with 994 over 1,000 equals p times 6 over 1,000. And with just a little algebra, if we were to multiply each side by 1,000, these would cancel out. And then we'd multiply each side by 1/6, or divide this 6 to the other side, and we come up with p equaling 994 over 6. That's what we have down here. And that is approximately $165.67. Now you should also add in the cost of the ticket that the player purchased. So you actually have to add $1 to this because the player paid $1 to get the ticket. So actually the state's payout should be $166.67 for the game to be fair. So it should be about more than double what they actually pay out. And this slide just describes what we had already discussed. So for the PA daily number, on average, you can expect to lose 52 cents for every dollar you play, or you can expect to only win back 48 cents for each dollar that you play. And that concludes our discussion about expected value.